Hello students, welcome to EPG Pathshala. I am Dr. Dinesh Kalyanasundaram from Indian Institute of Technology, Delhi, and I work in biomedical engineering. Today we are going to discuss about a module called complex number and analysis. So students, let us first understand how and what we are going to learn in this module. First we are going to understand the number system. Then we are going to understand what are complex numbers and what are their operators, how mathematical operations can be done. More than that, what we need is why we are going to perform this, and so we will have to understand what is the physical importance of the complex numbers. Then we are going to understand how the complex numbers in the coordinate system. And let's go to this introduction, and we will see a lot of problems in the field of engineering and medicine has a complex nature, okay, and needs more than one space to define the quantity. Okay. Now, this potential will have more than one dimension, and the dimensions are interdependent. Now, we want to understand what is interdependent, right? You might have seen the physical axis x, y, z many times. So, any number of times you would take a number in an y axis or an x axis, whatever operation you would perform or how many times you would multiply, it would never become another axis, right, until you are turning an object or something like that. But if you think about a complex number, the two axes are very interdependent, which means it can switch from one phase to another phase, and that's what interdependent means. Okay, and this has led to the complex number system, and we will see later why we need such a system. Okay, and one of the axes we are going to call it as a real axis, and one of the axes we are going to term it as imaginary axis. Okay, the word imaginary can be delusional because it's not completely imaginary, because it can always become a real number, okay, depending on what mathematical operation you are performing. So, we will first see what is a number system, then what is a complex number system, and then when to use it, then what is its physical significance, and we will also see a few solved examples related to this topic. Content. The first item is a number system, what we are going to deal about. The second is we are going to see what is the concept of I, which is indicated for the imaginary axis. Then we will see how the algebra, the addition, multiplication and all these will deal for the complex numbers, and how the complex number can be written in the polar form. These are the four things that we are going to focus on in the content. We are going to see the history of complex numbers. The complex number system was very first introduced, or the need was arised when people wanted to find the square roots of negative numbers. During it was first discovered or thought about in the 1st century by a Greek mathematician. Then later in the 16th century, the proper study of complex numbers arose when algebraic solutions of the roots for cubic and quadratic polynomials were analyzed and discovered. In the 18th centuries, then it gained much wider use as it was noticed that formal manipulations of complex numbers could simplify calculations of trigonometric functions. In 1730s, Abraham gave a very useful formula, and this is some of the formula which you might have to remember later in the due course of the your course. Okay. This is going to relate complicated identities, right? Especially when it was involving trigonometric functions. One such example is cos theta plus I sin theta to the power of n can be simplified and straight away written as cos n times theta plus I sin n times theta, right? So, instead of doing complex multiple operations, all we have to do is just find the cosine of n theta and sine of n theta. Okay. So, these kind of identities, what we call, has actually helped us to solve complex problems in a much faster and simpler way. In 1748, Euler, he went further to give us the most famous formula for the complex analysis, which is really, really important, where cos theta plus I sin theta can be written as exponential to the power of I theta. It can be denoted, and so this is another important aspect, and this something that you will or you would have probably used several times earlier, or maybe later you find it useful. Now we are going to see the number system. This is also going to be called as Venn diagram. So you want to remember that word Venn. It's not W-H-E-N, it is V-E-N. So what are natural numbers? Natural numbers are 1, 2, 3, all the integers which are positive integers, but not including 0. Then comes a bigger bracket which is called whole numbers, where it is the natural numbers with the inclusion of 0. Then we go to the bigger bracket and find out what are integers. Integers are both the positive and the negative integers, or the numbers or natural numbers, with including 0. So, these become integers. Please note that negative minus 3, many people tend to see that it is not an integer. It is an integer. The sign only means it is in a different direction. Then we talk about the second system, the more bigger system, which is called rational numbers and irrational numbers. In the rational numbers, actually the simple definition of any rational number is it can be written as a ratio of two integers. So, minus 3 by 8, these two are integers. Minus 2, minus 1. Minus 1 can always be written as minus 1 by 1. 0 can be written as 0 by any integer. It will give you 0. Right? Now, we have to completely understand the difference between rational and irrational. So, let me go to irrational numbers, and then we can see what is exactly the difference between rational and irrational. In an irrational number, these are numbers, or you want to identify or denote a quantity with two integers, but irrational numbers are there when it cannot be written as two integers. For example, you want to denote pi, pi which is 3.14416 and stuff. It is a non-ending number, and it cannot be completely governed by 22.7. 22.7 by 7 keeps on, the number is unable to meet or explicitly say the irrational number. Those kind of things where the sequence cannot be completely identified by using two numbers, two integers, then it becomes irrational. Now, let us go to 1 by 3, which is a rational number. Now, if you see 1 by 3, which is a rational number, it is 0.33333, but it is also an infinite series of 3's after the decimal point. Now, why 1 by 3 is called a rational number, but not 22 by 7? In 1 by 3, we know that it is a continuous 3's. Okay? So, we know what and where it is going. But in the case of 22 by 7, we do not know where it is tending to. So, this is another small difference between rational and irrational numbers. So, the first key point is it cannot be represented as a ratio of two integers, and the whole series is not known. Okay. So, then so this is the difference between these two numbers. Okay. And these two numbers are combinedly called as real numbers. So, technically anything in the world will come under real numbers. The same real number, if it is mentioned in the imaginary axis, so it just becomes imaginary number. Okay. So, the only thing is it is going to be represented with a small letter I. Okay. But otherwise, then the whole number systems what is going to be in the real axis or the real numbers will also be the same, but it will be in the different axis. Okay. Together it is completely called as the complex numbers. So, the natural or counting numbers are generally the 1, 2 up to infinity. So, the whole number systems are nothing but the natural number systems along with 0, right. And what are integers? Integers are the real numbers consisting of natural numbers and their additive inverses. So, additive inverses mean it is also in the negative regime. Okay. So, integers will always have the same number with no decimal points or any fractions. Okay. So, such as -4, -3, -2, -1, 0, 1, 2, 3, 4, 5. Now we will come to the next point, which is rational numbers. Rational numbers are those numbers which can be expressed as a ratio between two integers. Okay. For example, 1 by 3 is a rational number, minus 111 or 1111 by 8 is a rational number. Okay. Then if you are talking about rational number, then there is something irrational. And what do we understand about irrational? So, let us look at irrational. A irrational number is one that cannot be written as a ratio or fraction, which means the number or with the decimals, it is so complicated that no two integers can actually give that result. For example, 22 by 7 is a very good irrational number. So, 22 by 7, it just the numbers after the decimals keep changing and repeating and it never ends. Okay. So, you cannot exactly when you say 22 by 7, 22 by 7 is actually not capturing the 3.147, or for example, another example is put on your slide, -1 root of 5 by 2. Root of 5, you know, it is not an integer, right. And so, the sum on the top is not an integer. Okay. So, when you, so the two ratios is not is not integers on both top and bottom. So, it is an irrational number. And we are going to see the number system again. The real numbers is a set of numbers containing all the rational numbers as well as the irrational numbers. The complex number system is going to be the set real numbers, but represented in two different axes, right. So, it can generally be written as A plus I times B or B times I, where A and B are real numbers and I is the imaginary indicator that it is a unit, it is a different axis. But so, A and B can be all the numbers in the world, it can be rational number, it can be irrational number, it can be anything. The real numbers in the complex system are written in the form A plus 0 times I. The set of complex numbers is important because for any polynomial p of x with real coefficients, all of the solutions of p of x is equal to 0 will lie in the complex plane. In complex number system, we have an imaginary and a real part. Now, these two axes or parts or spaces, however you want to term it as, they are completely different, but they are interdependent. Okay. In the complex number system, imaginary part generally means that it is separated from the real part in terms of space or time. Okay. It is difficult to visualize the real and imaginary part simultaneously, but imagine there is an imaginary part which exists from time to time, or it is delayed by some time, or it is delayed by some space. Let us assume a snake, right. It has a head and a tail. If we consider at a point at any point where the snake is moving, either the head will appear or the tail will appear at a point, at a time or at a point, and then the other will cross at a later time or point. Okay, and but the total energy of the system, or total uh, 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 part of the system, or total enthalpy, or whatever you want to say of the system, it is only delayed by a few parameters like time or space. But as a system, it is still there, right? And they are both interdependent on each other. Okay, so the total energy of the system, consisting of real and imaginary part, is always conserved, but it is difficult to measure imaginary part, as it doesn't appear at the same time. We are going to see the concept of I. I denotes or separates the real and imaginary parts in a complex function or a variable. It has different interpretation in different fields. Topics utilizing complex numbers include the investigation of electrical current, wavelength, liquid flow in relation to obstacles, analysis of stress on beams, the movement of shock absorbers in cars, the study of resonance in structures, the design of dynamos and electrical motors, and the manipulation of large matrices used in modeling. In a DC circuit, voltage, current, and resistance are scalar, but is not the same in a AC circuit. These quantities, which now alternate in direction and amplitude, possess other dimensions, which such as frequency and phase shift, that must be taken into account. And the concept of I helps us to identify the frequency shift or the shift. In order to analyze AC circuits, it became necessary to represent multidimensional quantities. Complex numbers were used to express the two dimensions of frequency and phase shift. And we are going to see the concept of I in a more application oriented. So I am using an electric circuit to explain that. Don't get panicked. This is we are going to explain. We are not going to test anybody now. On the right corner, you are seeing a circuit which has a R, which is the resistance, and there is a L, which indicates inductance. So inductance actually happens in any coil. Okay, let's not go into the electric field, but let's understand there is a L, which represents the inductance, and then there is a capacitance. A capacitance is a circuit or electrical component which will hold on to the charges for a long time, and after sufficient amount of charges are accumulated, it will break the dielectric medium, which is seen as the blue color in between the two black plates. It will break into the medium, and then it will get the charges will flow into it, the other side of the circuit. This resistance or impedance. Okay, so we are going to use the word impedance because resistance is going to get allocated only for a resistor. Okay, so we are going to call it as an impedance effect. And as you know, across any form of resistance, there is going to be a voltage drop. Okay, or so we are going to see how much is the voltage drop across a resistor, which is indicated as a VR, and then there is a VL, and then there is a VC. As we know, this difference is going to be affected only when there is an alternating current. So the alternating current I of t can be written as Im times sine omega t. So Im is the amplitude and sine omega t is the shape of the or the sinusoidal effect of the signal. Okay, so this is called LCR circuit. Okay, and where there is an inductor, capacitor, and resistor connected in series. Series meaning one after the other. Okay, and it's connected to an AC power source. Now we know the famous formula V is equal to I times R, but that is only in a simple resistance based circuit. When you have other forms of resistance such as inductance and capacitance, you are going to write it as V is equal to I times Z. Z here indicates impedance, and that equations are given on the left bottom. Okay. So, the Z is going to be written as R times I XL minus XC, and what does R meaning? So, let us see the picture which is on the left center. So, the left side center of the page image actually indicates there is a VR and you see an I and you see the word real. So, that means the voltage drop VR which is happening on across the resistor, and there is a I which is a current which is flowing in the whole circuit I, is always in phase, and they are always in the real axis, or let us say in one axis. But when there is a voltage drop VL which is happening across the inductance L, okay, so there the current is going to lag behind, or in other words the voltage is going to lead. So, there is going to be a voltage which is going to get which is going to appear in time much faster, okay, and that is going to be represented on an imaginary axis. Remember, the imaginary axis, the whole enthalpy or the energy is still preserved, but just that when you are measuring resistance it just does not appear. So, it happens in a time which is ahead. So, we represent the VL 90 degrees earlier to coming to I, and that is why if you see in the equation Z is equal to R times I, and XL is in the positive direction, which means it is leading, the voltage is leading, and then there is XC which is because of the VC happening in the capacitance C, and there the capacitance is going to lag. So, that is why it is minus XC. So, it is only a matter how you want to have a phase difference between I. Phase difference here means spatial difference between I and the current and the voltage. So, the current is sinusoidal, which means it is going to change with respect to time, and the voltage is also sinusoidal, which is again means it is going to change with respect to time, right. So, the V can be represented as VR times I VL minus VC. It shows impedance leads to the lagging and leading voltage across the capacitor and inductor respectively. Using the complex plane, we can represent voltages across resistors, capacitors and inductors in a circuit, and most of the electrical circuits contain all the three or at least the first two. Now, how is it going to help us understand the voltage or the current is what we are going to see. The voltage across the resistor is regarded as a real quantity, okay, which means the voltage is in phase with the current, okay, while the voltage across an inductor is regarded as a positive imaginary quantity, which means when there is an inductor coil, the voltage is going to be shifted in time ahead and ahead of current, and that is what is called positive imaginary quantity. And then the voltage across a capacitor, we have a negative imaginary quantity. Negative meaning the voltage is going to lag the current by 90 degree. And how do we do that? It is by creating a imaginary axis and saying whether it is preceding the current or is it receding from the current. Okay. Another example is electromagnetism, and like all of you know, the electric field and magnetism cannot be separated. Okay. One always converts into another and the energy is stored in one form to another. So, electromagnetism is a very useful a field where complex numbers are used. Okay. So, rather than trying to describe an electromagnetic field by two real quantities, electric field and magnetic strength, it would be best we can describe it by a single complex number. So we know it is a package, okay, of which the electric current and magnetic components are simply real and imaginary parts. experimentally we can think of the real part as the active power, okay, and imaginary part as the reactive power, okay, and in the circuit. Okay, so what is active power? Right now what we have, that's an active power, okay, and something that we may get later in time or space, then it becomes a reactive power, okay. And since we can measure the resistance across a resistor, it is more in the active power, but we can't measure the resistance across a capacitor or inductor, okay. But however, it will create an effect affecting the power. Now we have to come up with a way to find out that resistance which is created in a capacitance or inductor, right. And that is why we say, okay, it is affecting, but it is affecting in a different plane or a different axis or in a different point of field, and so those things are generally called as reactive power. We are going to see algebra of complex numbers. On the right side, you are seeing the image of representation. There are two complex numbers, Z1 and Z2, and you can then you are seeing the vector addition of Z1 plus Z2, or you can see the vector addition of Z1 and minus Z2, okay. So that is equivalent to considering it as Z1 minus Z2 or adding Z1 plus of minus Z2. We can represent the complex Z as A times Bi or A times Ib, it does not matter, and Z is equal to C plus Di, the two complex numbers. The formula for addition is Z1 plus Z2 will be simply addition of the real numbers A plus C and the addition of imaginary numbers B plus D times I. The subtraction is again going to be the subtraction of the two real numbers A minus E and the subtraction of two imaginary numbers B minus D times I. In case of multiplication, this is the most important thing. Z times Z1 is going to be A times Bi and C times C plus Di. It's going to be A times C, which is the real number, minus B times D, okay. And this is the critical factor of when an imaginary axis is getting transformed into a real axis, okay. I, as you know, is root of minus 1. So root of minus 1 times root of minus 1 becomes minus 1, and that when multiplied by B into D becomes minus BD, and that transforms into the real axis. So it is AC minus BD. Then in the real imaginary axis, you will have anything multiplied between a real number and a imaginary part. So Bi into C will give you BC, and A times Di will give you AD times I. So BC plus AD will become the imaginary part. In the division, this is a second thing that you might want to learn how to do this. When we have Z1 by Z2, which is A plus Bi divided by C plus Di, there is something called conjugate. Conjugate meaning we only change the sign of the imaginary number, okay, and we are going to do that only for the denominator, right. We are going to take C plus Di, which is the denominator, and what is the conjugate of C plus Di? It's going to be C minus Di, and we are going to multiply C minus Di, okay, and divide it by C minus Di. So technically it cancels out, but so there is no change in the values. So we are going to see how this operation of multiplying and dividing by the conjugate of the denominator is going to help us. So we are going to apply the same formula of multiplication. So now since it is C minus Di, it's going to become AC plus BD, and that is going to be in the real time, and in the imaginary axis it's going to be it is going to be BC minus AD Okay. Now, the denominator of the real part as well as the imaginary part, if you see, is going to be c squared minus of d squared times I squared. I squared is minus 1. So, it actually becomes minus d squared into minus 1 becomes plus d squared. So, it is c squared plus d squared. So, both the real and imaginary parts are going to have the denominator as c squared plus d squared. We are going to see how we can represent the real and imaginary parts of the complex number in a different form, right. We can always write a plus ib. How can we represent it in a different form? So, that is the polar form of the complex number. So, right side you see an image. Okay. So, this is equivalent to x, the point dark black circle is equal to x times on the real axis and plus y times I, which means it is on the imaginary axis. Now, we can also represent that particular point or value in the complex plane by denoting the distance from the origin and mentioning the angle phi. Is it right? So, that is what is going to be called polar form. In polar form, we represent a point or value in the complex system by magnitude, that is the distance from the point and the origin, and an argument. Okay. So, this is a key word in complex numbers. We say argument. Okay. What is argument? That is just the angle which is with respect to the real axis. Okay. How much is the angle made to the real axis in the counterclockwise direction. So, you always take the real axis and you are going to move counterclockwise. And we are going to see polar form of the complex number and we are going to calculate it further. Okay. Like we discussed in the previous slide, we can represent any value with a amplitude and a argument theta. So, what is r? What is the value of r? R has to be the distance between 0 to the point. So, it can be easily written graphically. You can see it is x squared plus y squared to the power 1 by 2. It is the root of the distance. It is a right angle triangle and it is the hypotenuse. The argument or the angle can be actually seen that it can be done as the tan inverse of the height, which is the y value, okay, to the x value, okay, and that is why it is tan times y by x, value of y by x. In the polar form, it can be represented as the complex number z is equal to r times, which is the amplitude, times cos theta cos phi plus I sin phi. The same complex number can be represented in modulus angle form as well, okay, where you can just write z is equal to r and then the angle symbol and then just say phi. In the Euler form, it can be just written as z is equal to r times e raised to the power of I phi. And we are going to see what is the complex conjugate of a complex number. What is the physical interpretation? So, on the right side figure, you are seeing the z, what we were seeing all the time. And what is the complex conjugate? It is just the reflection of the point z, okay, over the real axis. That means you just flip z and keep a real axis same, and then you will get z is equal to x times I y. Okay. So, that is the reflection. So, we are going to now see how we can solve some of the problems. Okay. So, we are going to see solved examples. So, let us do some mathematics with. So, what is 1 plus I divided by 1 minus I? Now, as I said, we have to multiply by the conjugate and divide by the conjugate of the denominator. The denominator is 1 minus I, the conjugate is 1 plus I. So, we multiply and divide by 1 plus I on both sides, on the top and the bottom. So, the top one it will give rise to 1 plus 2 times I minus 1 divided by 1 plus 1, okay, and then when you do the mathematics, it becomes just I. The second question, what is I raised to the power 2012? Okay, we know that I squared is minus 1, and we know I power 4 is plus 1. Okay, so I times 4n will always become a positive integer. Now 2012 can be written as I to the power of 4 times 503. So once it is 1 power 503 will always be 1. And we are going to see another example problem. Find z where z squared plus z dash squared is 0, and z dash is a complex conjugate of the number. Okay, so let us assume, because we need to find what it is. So x plus yi, let us assume that z is equal to x plus yi, then z dash or conjugate is going to be the reflection, which is x minus yi. So z squared plus z dash squared is equal to 0. That means if you do the mathematics expansion, you will find it is going to be x squared minus y squared plus 2ixy, which represents z squared, and conjugate squared is going to be minus of x squared minus y squared minus 2xiy. Now this allows us to make it 2x squared minus 2y squared is equal to 0, or in other words, x plus y into x minus y is equal to 0. So the solution can be x is equal to y, that is one form of solution, or x is equal to minus y, or y is equal to minus x. So the z can be any number x. So z can be just x times ix, and x can be any number, or it can just be written x as common factor and 1 plus I, and x is equal to x, or x is equal to x minus ix, or you can take the common factor x out and just say 1 minus I, and the x can be any real number. We are going to find a rotation of a complex number. So let's see in the graph, there is a point P, right, in the plane, and we are going to rotate it about O, which is the center origin, by angle pi by 3. The new position is P dash. Now we will have to calculate what are the coordinates of P dash, and we are going to see the solution to the problem. The figure is given in right bottom. So let us say the P represents the complex number z, okay, which has a polar notation r times cos theta plus I sin t. Now if you rotate it by pi by 3, what is going to be the new P dash? It is simply going to be, you will have to simply just multiply by cos pi by 3 plus I sin pi by 3, the additional rotation that you are going to perform. So now you know how to do cos times cos, and a real it's a complex number multiplication. So if you perform the multiplication, end of the day you will see, hence P dash will just be or cos times t plus pi by 3 plus I times sin t plus pi by 3. In other words, what are we trying to say is, a complex number, if you are going to just rotate, you just have to add the argument to the existing angle, and so it's very simple and straightforward. So students, let us summarize what we have learnt in this module. In this module, we have learned what are all the various number systems, okay, focusing on the what is a complex number system and what is it physically interprets, or physical interpretation of the numbers. We also saw what is the concept of I in electrical systems and magnetic systems and other fields, and how it can be physically represented. Then we also learned how to manipulate the complex numbers and its various properties of the complex numbers. And we also saw what are the different forms it can be represented. And I hope you enjoyed the session, and thank you for your kind attention.